This is Dharamvi sir here. So today we are going to continue with chapter 9 of grade 12 maths, which is differential equations. And the topic of today's video is homogeneous differential equations. So first let me tell you about homogeneous differential equation. So differential equation that can be written in the form of dy upon dx equals to fxy, that is function of x or y, or dx upon dy is a function of xy. If dx upon dy it should be a function of xy, if it is dy upon dx it should also be a function of xy. Okay? Then, and the condition is that fxy and gxy are homogeneous functions of degree 0. Okay, the degree of f and g, that is functions of x and y, should be 0. Then it is called a homogeneous differential equation. And coming to how to solve a homogeneous differential equation. So if we have equation of the type dy upon dx equals to function of xy, then we make a substitution y is equal to vx and solve. Remember that if it is dy upon dx, that is function of xy, then we take y is equal to vx, and if it is dx upon dy, then we take the substitution x equals to vy. With this, let's start exercise 9.5. So show that the given differential equation is homogeneous and solve. And the question 1 is x square plus xy dy equals to x square plus y square dx. First we have to show that this is a homogeneous differential equation. So taking dy upon dx, we are getting x square plus y square upon x square plus xy, and taking x square common, we will get x square 1 plus y square upon x square 1 plus y upon x. So x square will be cancelled, these two are cancelled, so we get dy upon dx as 1 plus y upon x whole square upon 1 plus y upon x. So it is a function of y upon x. So dy upon dx is a function of y upon x. Therefore it will be a homogeneous differential equation. So putting y upon x equals to v, we get y is equal to vx. We had to put, remember that dy upon dx, so y is equal to vx. So we get dy upon dx equals to v plus x dv upon dx. So making this substitution equation 2, we get v plus x dv upon dx equals to 1 plus v square upon 1 plus v. So transposing, we are getting x dv upon dx equals to 1 plus v square upon 1 plus v minus v, or x dv upon dx equals to 1 minus v upon 1 plus v. So separating the variables, we are getting 1 plus v upon 1 minus v dv equals to dx upon x. So integrating both sides, we get integral 1 plus v upon 1 minus v dv equals to integral 1 upon x dx. Now we have learned lots of integration in chapter 7, so we can simply integrate this. So on simplifying, we are getting integral 1 plus 1 minus 1 plus v upon 1 minus v dv equals to log x plus c, which is the differential of 1 upon x. So differentiating this, we are getting minus 2 log 1 minus v equals to log x plus c. But we have v is equal to what? Y upon x. So putting the value of v, we get minus 2 log 1 minus y upon x minus 1 upon x equals to log x plus c. So simplifying, we will get the solution of the given differential equation as x minus y whole square equals to cx e power minus y upon x, where c is the equals to e power minus c, which is the constant of integration. Moving to question 3, show that the given differential equation is homogeneous and solve it. First we have to show that this is homogeneous and then we'll solve it. So we have the given differential equation as x minus y into dy minus x plus y in dx equals to 0. So first we have to prove it homogeneous. So finding dy upon dx, we are getting dy upon dx equals to x plus y upon x minus y. Taking x common, we have x into 1 plus y upon x into 1 minus y upon x. So x and x will be cancelled. we get dy upon dx equals to 1 plus y upon x, 1 minus y upon x, which is a function of y upon x. Therefore, dy upon dx is equal to function of y upon x. Therefore, it is a differential equation which is homogeneous. So first part is done. Now, since we have dy upon dx, so we will take y is equal to vx. So dy upon dx equals to v plus x dv upon dx. So making these substitutions, we get v plus x dv upon dx equals to 1 plus v upon 1 minus v. So separating the variable, we have learned separating the variable in the previous video. So taking x to one side and dv to one side, we get 1 minus v upon 1 plus v square dv equals to dx upon x. So integrating both sides, we have integral 1 minus v upon 1 plus v square dv equals to integral 1 upon x dx plus c. So taking this into two parts, we get integral 1 upon 1 plus v square dv minus v integral 1 plus v square dv, integral 1 upon x dx log x. So this becomes tan inverse v. This is multiplying 2 and 2, we get half integral 2v upon 1 plus v square dv, 2x plus c. So tan inverse v minus half log 1 plus v squared log x plus c equals to this one. We are using this property, integral f dash v upon fv dv equals to log fv. But we have v is equal to what? Y upon x. So putting the value of v, we get tan inverse y upon x minus half log 1 plus y square upon x square log x plus c. So simplifying this, we will get our solution as tan inverse y upon x is equal to half log x square plus y square plus constant c, which will be our required solution. So next is question 5. Show that the given differential equation is homogeneous and solve it. And we have the differential equation as x square dy upon dx equals to x square minus 2y square plus xy. First we have to show that this is homogeneous. So dy upon dx equals to x square upon x square minus 2y square upon x square plus xy upon x square. So we get the value of dy upon dx as 1 minus 2 y upon x whole square plus y upon x, which is a function of y upon x. Therefore, the given differential equation is homogeneous. So putting y upon x equals to v, we get y equals to vx, or dy upon dx equals to v plus x dv upon dx. So putting these values in the given equation, we get v plus x dv upon dx equals to 1 minus 2v square plus v. Or separating the variables, we are getting dv upon 1 minus 2v square equals to dx upon x. So integrating both sides, that is integral 1 upon 1 square minus under 2v square dv equals to integral 1 upon x dx. So we are applying the property integral 1 upon a square minus x square dx equals to 1 upon 2a log mod a plus x upon a minus x. We get 1 upon 2 into 1 log 1 plus under 2v upon 1 minus under 2v equals to log log x plus c. So putting v is equal to y upon x, we get 1 upon 2 root 2 log 1 plus root 2 y upon x, 1 minus root 2 y upon x equals to log x plus c. And simplifying this, we will get our solution as 1 upon 2 root 2 log x plus root 2y upon x minus root 2y equals to log x plus c. So moving to question 7, show that the given differential equation is homogeneous and solve. And the given differential equation is x cos y upon x plus y sin y upon x into y dx equals to y sin y upon x minus x cos y upon x equals to x dy. So it is already given that it is y upon x. We need to find dy upon dx. So finding dy upon dx, we get x cos y upon x plus y sin y upon x into y upon y sin y upon x minus x cos y upon x into x. So opening the bracket, we get xy cos y upon x plus y square sin y upon x upon xy sin y upon x minus x square cos y upon x. So dividing the entire RHS by, that is the numerator and denominator, by x square, we get dy upon dx is equal to y upon x cos y upon x plus y upon x whole square sin y upon x upon y upon x sin y upon x minus cos y upon x, so which is the function of y upon x. Therefore, the given differential equation is homogeneous. So putting y is equal to vx, we get dy upon dx equals to v plus x dv upon dx. So putting these values in the differential equation 1, we get v plus x dv upon dx equals to v cos v plus v square sin v upon v sin v minus cos v. So separating the variables, we are getting v sin v minus cos v upon v cos v to dv equals to 2 dx upon x. So integrating both sides, we get integral v sin v minus cos v upon v cos v dv equals to 2 integral 1 upon x dx. Okay, so using a minus b upon c, that is property of fraction, very simple. We get integral v sin v upon cos v minus cos v upon v cos v dv equals to this one. So we have integral tan v minus 1 upon v dv equals to 2 integral 1 upon x dx. Integral of tan is log sec v, 1 upon v is log v, 1 upon x is log x, and since all are logs, we are taking the constant of integral as log c. So on simplification, we are getting the solution as sec v is equal to mod c x square v. So putting the value of v is equal to y upon x, we get sec y upon x equals to cxy, where c is the constant of integration. So on simplification, we are getting the solution as xy cos y upon x equals to 1 upon c, which can be put as c1. So this will be the required solution. Moving to question 9, show that the given differential equation is homogeneous and solvable. And the given differential equation is y dx plus x log y upon x dy minus 2x dy equals to 0. Since we already have y upon x, so we need to find dy upon dx. Finding dy upon dx, we get dy upon dx equals to y upon x 2 minus log y upon x, which is clearly a function of y upon x. So therefore it will be a homogeneous differential equation. So putting y upon x equals to v, or y is equal to vx, we get dy upon dx equals to v plus x dv upon dx. So putting these values in the given equation, we get v plus x dv upon dx equals to v upon 2 minus log v. Now we have to separate the variables, taking v one side and x to the other side. We get 1 upon v log v minus 1 minus 1 upon v dv equals to dx upon x. So integrating both sides, we have integral of 1 upon v upon log v minus 1 minus 1 upon v dv equals to log x plus log c. So integrating this, we get log of log v minus 1 minus log v log x log c. Here we have used the property integral f dash d upon f b dv equals to log of f b. So simplifying this, we are getting log v minus 1 equals to cxv. Now replacing v by y upon x, we get log y upon x minus 1 equals to cx into y upon x, which is equal to log y upon x minus 1 into cy. So this is our required solution. Moving to question 11, for the differential equation, find the particular solution satisfying the given conditions. So we have to remove the constant of integration because we need to find the particular solution. So the given differential equation is x plus y dy plus x minus y dx, and conditions are y is equal to 1 and x equals to 1. First we need to find the differential, whether it is homogeneous or not. So finding dy upon dx, we get dy upon dx equals to minus x minus y upon x plus y. Since we are finding dy upon dx, so we need to find in the terms of y upon x. So taking x common, we get x y upon x minus 1 upon x y plus x upon 1. So x and x will be cancelled. So dy upon dx equals to y upon x minus 1 upon y upon x plus 1, which is clearly a function of y upon x. Therefore it will be a homogeneous differential equation. Supporting y is equal to vx, that dy upon dx equals to v plus x dv upon dx. So putting these values in the given differential equation, we get v plus x dv upon dx equals to v minus 1 upon v plus 1. Clear? So separating the variables, we are getting v plus 1 upon v square plus 1 dv equals to minus dx upon x. Integrating both sides, we have integral v upon v square plus 1 dv plus integral 1 upon v square plus 1 dv equals to minus 1 upon x dx. So simplifying this, we will integrate to find the value as 1 upon 2 log v square plus 1 for the first part, tan inverse v for the second part, 1 upon x is log x, and constant of integration is c. So again we have used the same property that integral f dash b upon fb dv equals to log fb. So putting the value of v is equal to y upon x, we get the solution as half log x square plus y plus tan inverse y upon x equals to c. Here we have a condition given that y is equal to 1 when x equals to 1. So putting these values in the equation 3, we find the value of c as 1 upon 2 log 2 plus 5 by 4. So putting this value in equation 3rd, we get 1 upon 2 log x square plus y square plus tan inverse y upon x plus half log 2 plus pi by 4. So simplifying, we will get a final particular solution as log x square plus y square plus 2 tan inverse y upon x plus log 2 plus pi by 2. Moving to question 14. For the differential equation, find the particular solution satisfying the given conditions. And the differential equation is dy upon dx minus y upon x plus cosec y upon x equals to 0, and the conditions are y is equal to 0 when x equals to 1. So since already y upon x is given, so we need to find dy upon dx again. So dy upon dx becomes y upon x minus cosec y upon x, and it is clearly a function of y upon x. Therefore it is a homogeneous differential equation. Since we have dy upon dx, so we put y is equal to vx. So dy upon dx equals to v plus x dv upon dx. So putting these values in equation 1, we get v plus x dv upon dx equals to v minus cosec v, or x dv upon dx equals to minus 1 upon sin v, and separating the variables, we are getting sin v dv equals to minus dx upon x. So integrating both sides, we have integral sin v dv equals to minus integral 1 upon x dx, and we know that integral sin is minus cos, integral of 1 upon x is log, constant of integration is c. So simplifying this, we are getting cos y upon x equals to log x plus c. We have already put the value of v is equal to y upon x. Now we have to find c. It is given that y is equal to 0 when x equals to 1. So putting the value of x and y, we are getting c is equal to minus 1. So putting the value of c in equation 2, we get cos y upon x equals to log x plus 1, which is equal to log x plus log e. 1 equals to log e. So simplifying, we are getting the value as cos y upon x equals to log ex, which is the required particular solution. So with this, we end the exercise. So solve the remaining sums, and don't forget to solve the examples given before the exercise. Thank you and all the best.